Alright, hell yeah, this is going to be cool. So we have statics, and this is Hibbler. And this is a problem where you have a force, and then you have to find the moment about this force. And so we're going to talk about that, and we're actually going to use the dot product. You know, usually you use the cross product to find a moment. We're going to do the dot product. And it was a challenge, because right here it said, hey, it would be really difficult to find the perpendicular distance from O out to this force. We know this force is 2 kilonewtons, so if we just knew the perpendicular distance, we just multiply those two numbers together, and then we could actually get the moment that's required to drive this tree over. So I guess I just showed you kind of the answer, but we're just going to go over just kind of one aspect of this problem. So what I need is this perpendicular distance. So from O, I can come over here and then kind of just draw a perpendicular line. And so how the dot product works is like, hey, I have this distance vector from O to A, and cool. And then I also have, you know, I can treat this as like a distance vector as well from here to there. And if I want to dot, you know what I mean, like let's say this distance vector with this distance vector, well, we're going to get a couple things. And I should reframe this. The dot product of two things is still multiplying those things together. So if I have like, hey, this is 12 and I don't know, maybe this is like 15 or 20 or something like that. If I take 12 and 20, well, heck yeah, I'm going to multiply those two numbers together. The most they can be is the numbers multiplied. The least they could be is if this distance is perpendicular to this distance. The dot product would be 0. And then you can just see it's about a 45-degree angle. So if I multiplied 12 maybe by 20, I would also... A 45-degree angle is like the cosine of 45 is 0.7. That's like 70%. So I'd have to take 12 times 20 and then just take 70% of that. So what we're going to be doing is using unit vectors. So it's kind of tricky, but here's kind of the scenario that we're going to be using. We know this is 12 meters. Cool. And then we're going to get a unit vector in this direction. This problem can be kind of simplified because we know that this is the only component for this distance, and it's k hat. You know, it's in the z direction. So when we go to do our dot product, we'll have 12 k hat dotted with whatever the other vector is, but only the k component of that will be needed. So, and there's two ways to do it. I might do the other way at the end where you consider this a unit vector. We could say, hey, I'm going to have a unit vector of 1 dotted with this unit vector, and then I would have, it would just be 1k multiplied by the unit vector over here. And what you get is you get that percentage. You get the percentage of this unit vector that's along this line. If with the dot product, if these two are going in the same direction, heck yeah, it's 100%. And you can see here that the cosine component is going to be less. And if this is a 45-degree angle, again, it's going to be like 70%. So that's kind of what when we actually do the problem, we're going to be looking for those values. Okay, hell yeah. But this is not the distance we want. Cool. We know that, let's say this is a unit vector. Let's say it's 12, so if we know this is 12, cool, this distance is going to be 70% of 12. Heck yeah, so that's just going to be 12 times that number, and we know this distance. We really want this. This is the perpendicular distance, but then we just use Pythagorean's theorem. So, hell yeah. Alright, so let's go through that whole process in hopefully the simplest way possible. So I have a distance vector of 12, like a magnitude of 12 in the direction of the z-axis. So we multiply it by a unit vector in that direction. Cool. And I'm going to dot it with, but I need the unit vector of this. So this thing has 3 components. If I start up here, well, I'm going to be going in the x direction 4. I'm going to be going in the y direction 12, and I'm going to be going in the z direction 12. Okay, but I'm going to have those three components, and I got to divide by the magnitude of them. But when I do the dot product, all I'm going to be dotting is k dot k. That's the only thing. If you have a vector in the k direction dotted with a vector in the k direction, that's 100%. Cool. So we're going to have 12, but this component, so in the k direction, this has a component of 12. So I have 12k, but now we're going to, this distance vector, we're going to divide by its magnitude. Its magnitude is its component squared. So, cool, here's a component, 12 squared. Here's, well, I should have done the x component first, but 12 squared plus 4 squared plus 12 squared. That's, to get from here to there, that's all the components. It's 4, 12, and 12. Cool. And then so when we dot this, the k dot k, again, just becomes 1. It's 100% or 1. And then we get everything else as a scalar. So, so cool, let's do it. So we're going to have 12 times 12, and then we're going to divide by the square root of 12 squared plus 4 squared plus 12 squared. And the tricky thing about doing this is like kind of keeping up to be like, what are we doing? You know what I mean? Like what? Like again, so we have this vector and we're dotting it with the unit vector, and I only have to dot it. You know, this has other components, an I and j component, but if I'm dotting and I only have one over here, I can only dot, I can't dot k and I. Those are perpendicular, so that's another way to look at this. If we have I, j, and k, and I have a vector in the k direction, a vector in the I direction, if I dot these, they're perpendicular. So I can multiply the two numbers together, but then I have to multiply it by the cosine of 90, which is 0. So, you know what I mean? There you go. All right, so so let's push the button, and what do I get? I get this distance is 8.2589. So now I need just this distance d. That's the one that I wanted all along. Well, I use Pythagorean's theorem. Pythagoreans said this is a, b, and c. I'm going to go over this because we got a squared plus b squared is equal to c squared. Cool. What we know is one of them. Let's say we know a, we want b. You know what I mean? And we know what c is. C is 12. So if I want b, rearrange this equation, we're going to be b is c squared minus a squared square root. So, hell yeah. If you know the hypotenuse and a side, just remember it's like hell. Hypotenuse squared minus the side squared. I mean, you can't be bigger. You know, you got to minus it. So it's kind of easy to see this minus and remember that if I have this minus this must be the hypotenuse. This must be one of the other sides. And I must be trying to find the side because I'm taking the square root of it. All right, booyah. So we have 12 squared minus... I'm going to store this, well, I'm going to store that value in my calculator as x. So we have 12 squared minus x squared, and then we're going to take the square root of that. Oh, whoa. I didn't do it right. 12 squared minus x squared, take the square root of that, and we get a distance of 8.705. So that's the perpendicular distance. If I multiply by 2 kilonewtons, then I get the moment, and it's going to be 8.705 times 2. Now for this problem, they were using Cartesian coordinates anyway, so they use the cross product and they get down to here. So if you have two, if you have anything with like, hey, this direction and that direction, what's the magnitude? You know what I mean? Same thing. It's like this is Pythagorean's theorem. Maybe this is negative 16.5 and this is 5.51. And so what would be this vector? Well, it's just taking the square root and then squaring these. So we got 16.5 squared plus 5.51 squared. And we get 17.4. They rounded the hell out of this, you know what I mean? So it's, but it's close enough, 17.4. So that's one method to get the perpendicular distances. And I think it's really useful to know how the dot product and the cross product are related. Because you could have also done the same thing by doing unit vectors, and then you could do the same thing with the cross product. But it's kind of just interesting to use the dot product to get that job done. Alright, I think we're going to do it one more time just because it'll really kind of explain maybe what's going on. So now what we're going to do is I'm going to turn this vector of 12k into a unit vector. So if this vector is 0, 0, 12k, so this is the j, this is the I component, well, the magnitude is going to be the square root of 0 squared plus 0 squared plus 12 squared. Cool. It's going to have a magnitude of 12. To get a unit vector, you got to take all of these and then divide by the magnitude. 0, 0, but then this is going to be 12 divided by 12. Cool. The unit vector for something just in one direction is just 1. You know what I mean? So there you go. So there's going to be this vector, the unit vector, and then we're going to get this as a unit vector. And we're going to do it, so I have 1k, and we're going to dot it with this unit vector. And we're going to write it out. So we have a distance of 4 in the k direction. I'm sorry, a distance of 4 in the I hat direction. This would be the j hat. And I don't even think you're supposed to actually put... Let's see, I'm doing this wrong, and I'm going to make other videos on this, because I just thought I, J, and K were just directions. I graduated without really understanding the unit vector. I think they taught the unit vector for like one class and just expected you to know it like all the way through. No one retaught the unit vector. No, a unit vector is a vector. This is a vector. You got to put an arrow and make a magnitude of 1. That is what you're talking about. It's a vector, sure, in the x direction, but if you don't actually do the vector, I think you're missing out on life. So, booyah. All right, so yeah, you have to take this distance 4 and then divide it by the total magnitude of this thing. So we're going to have 4, 12, and 12. So 4 squared plus 12 squared plus 12 squared. And we're just going to do this about 3 times. So that's the I direction. The J direction is 12. And sometimes I just do this. Just do the square root. You could do this, you know what I mean, kind of. And it's the same thing. And then we're going to do the K direction. And I guess it's important to figure out what direction our vectors are going. So, I mean, if we're starting up here, like, it would probably make the most sense because that's where the vectors kind of meet. And so this is going to be -4, 12, and then -12. So I'm going to have a -12 here, and then that square root. This is going to be the k hat. This is going to be the j hat. Now, if I say this vector should be in the downward direction. So we're going to say it's -12k hat divided by a magnitude of 12. This one's going to be -1k. So I'm just going to switch that over there. Okay, so now you can see that when we do the dot product, what we're getting is like we have a unit vector this direction, vector of 1, a unit vector this direction of 1, and when we dot them, we get this perpendicular distance. So let's blow that up. So we have a vector down of magnitude of 1, a vector this way, it's kind of got 3 different directions of magnitude of 1, and we want to draw a perpendicular line to this. So this really hones in this percentage, you know what I mean, because the percentage, or the fraction of a whole, let's say this just looks like 85%, who knows, you know what I mean, maybe 89%, who knows. But anyway, so if this is 89% of what? Of the hypotenuse. So that's what kind of a right triangle is you have a hypotenuse, and your sides are percentages. We actually want to know what percentage this is. And then once we know the percentage, then we can multiply that by 12. So we want 12 times the percentage, and I'm going to say this is the sine component. Because when we have the cosine component says, hey, if I have a vector this way and a vector this way, the angle between them is related to, well, never mind. The angle between them has a sine component and a cosine component. But when you do the dot product, it says, hey, this is the angle between them, and it's related to this component, the cosine component. And it's just really useful like when you have unit vectors, because you can see that, hey, these two vectors aren't in the same direction. If they were, I would multiply 1 by 1. We'd have 100% or just 1. But because we do have a slight angle, I'm multiplying 1 I'm multiplying 1 by 1, but it's representative of just kind of this horizontal or the shadow component of this 1 in that direction. And so it's like 1 times 1, but then the cosine of the angle. And so if this is the hypotenuse of 1, hey, the cosine of this angle represents this distance of maybe it's 0.89. I have no idea. Cool. So that's what this does. A unit vector dotted with a unit vector gives you, like literally just gives you this, the cosine of the angle, which is the percentage, kind of the fraction of the hypotenuse. So then, whatever the hypotenuse was, it just gives you this distance. Now, it isn't the distance that's going to be the driving, this distance is going to be what's driving the moment, kind of a force divided by a distance. I have a force out here and a perpendicular distance. So we're just finding first the other component, but then you can use Pythagorean's theorem that says the hypotenuse squared minus this side that we're going to find, maybe it's 0.9 squared, square root that. That's going to be this component, you know what I mean? So, cool. Well, let's do it. So, and just in our calculator, so we're going to have negative 1 multiplied by negative 12 divided by the square root. So it's kind of that same thing that we just did, like almost identical, instead of just multiplying by negative 12. So we're just doing this part first. Negative 1 multiplied by negative 12, but divided by 4 squared plus 12 squared plus 12 squared. Cool. So we get this ratio. It's 0.68. Who knew? And no duh. This is about a 45. I don't know what my mind was going blank. This is where the skills happen, where you just can intuit things. You know what I mean? Hey, I just went through talking about how this is a 45-degree angle, and then your cosine and your sine components are going to be pretty close to 0.707. So no duh. I should have just thought, well, what side of is it going to be 0.69 or is it going to be 0.72? You know what I mean? And so we get 0.688. And that's basically, this is 68.8%. Okay, sweet. So we can do Pythagorean's theorem even just right now. So I'm going to have 1 squared minus 0.688 squared, and then the square root that. And then that's going to pop out this percentage. So I'm going to have the square root of 1 squared minus this answer squared, and booyah. So we get 0.725, and now that's the percentage of this unit vector in that direction. Well, this unit vector can be represented as if we represent this as now negative 12 or just 12, that whole distance multiplied by this 72.5%. Well, that's going to give us that sine component. It's going to give us that distance that's going to be the driving force for this force being a moment arm. So hell yeah. So we're going to multiply that by 2. I'm sorry. I don't know what I was saying. We're going to multiply that by this 12. So this is the distance, and this is the percentage. 75% of this 12 is this distance. So we're going to multiply this by 12, and we get that 8.705. But yeah, I just thought this was a funny deal when the book, because it doesn't go over stuff like that. I love how sine and cosine are related, and it's kind of like this full circle. You know what I mean? You can, and it's just interesting how sometimes doing the dot product to get that ratio, to get that percentage, and then you can skip over to get the other one just using Pythagorean's theorem. So it's just, I don't know why more textbooks don't go through that full circle. because it's just really, yeah, because they say right here, notice the difficulty that would arise in obtaining the moment arm D. Well, sure. I mean, that is a, like, to think through that, but there's a lot of problems where this is super useful in kind of knowing that. And so I'm going to end by saying, sure, that's a difficult task, but so is doing the cross product. The only reason the cross product doesn't become difficult is because, like, there's like 5 different ways to do it. You can do it matrix style, you can do it right-hand rule style, you know what I mean? A lot of things require cross products, so you're just always going to be doing this. Where what we did today, just trying to find a perpendicular distance, that's a rarity, you know what I mean? And it requires knowledge of just like, well, how many different ways could we find this perpendicular distance from there to there? Well, we could actually use the sign. I'm going to make a separate video on that, because this one was just about using the dot product. And so, alright, so I think I'm done, so thanks for joining me, and that's the video.